Hello. Um, Once again, we uh, get together for this lecture in the software engineering series. This lecture is about, in fact, the whole week is about architectural design. So we look at a few topics here, looking at what sort of architectural design decisions we have to make when designing software architecture, and how do we express that architecture, namely documenting and representing these architectures using what we call viewpoints and views. We talked about that a little bit last time. Then representations of architectures, how you might represent those architectures. Patterns in architectures, sort of standard or often used patterns for certain types of systems that are useful as starting points for implementing or instantiating other specific architectures. And finally, something about application architectures. I'd like to recommend at this stage that before we proceed, if you haven't been through the slides, that you actually try to go through the presentation before listening to this explanation. Right, what is software architecture? It's software systems architecture. We have here the design process and its result for identifying subsystems for a big or an entire software or information systems. Because I think we can say the same thing about systems architectures as well, in terms of just not the software, but the entire information system. So subsystems making up a bigger system, and the framework for the control of subsystems and communication between its parts. As in any system, you would have studied that before. Actually, let me show you that slide now. Maybe you studied a little bit about systems theory, whereby systems are composed of subsystems, and these subsystems interact and collaborate to achieve a certain mission for the supersystem. So we want to express this architecture of the system. What are the main components and how they interact, and what do they interact? What do they exchange during the interaction? Right. So every subsystem in the software may contain one or more applications, components, or application units, parts of applications, for example, or databases, or whatever, things that are necessary for the whole system to operate. So the output of the design process is a description of the software system architecture, but also, as I said, sometimes we have to represent the entire information system architecture, and the software is one such component. And if you're interested in reading more about that, you need to follow up on this topic. Maybe look under the heading Enterprise Systems Architectures or Enterprise Architectures. Right. When do you get architectural designs? When do you care for architectural designs? Architectural design is the first stage of system design or software design. You start doing this immediately after or during the last bit of requirements analysis and specification. Some people call it the twilight between analysis and design, or requirement specification and design. So the architecture actually links the specification you've agreed to with your team and your stakeholders and the design. Sometimes we carry it out in parallel with some specification activity. In fact, when you specify a system and say, okay, this is the sort of shape of the system I want, you're in fact doing high-level design or architectural design. In designing the architecture, we identify the major system components and their interaction and their communications. At this stage, obviously, you can do like quality checks and validations to make sure that this system satisfies the requirements and that it actually would work to deliver the functions expected of it. So it's a nice stage we're not getting too much into the details and the nitty-gritty how the system is going to be implemented. You're adopting like a top level, high level view, bird's eye view, and you're making sure that these early designs, these sort of coarse grain designs, can actually deliver the functions you want to deliver to your stakeholders and users. One very important aspect about architectural design, and indeed the models in general that we've been talking about before, model and software engineering. The architectural design is one vital tool, one vital modeling tool to support communication, negotiations, and discussions between the stakeholders, or among the stakeholders and the developers. You negotiate to show your stakeholders what sort of system shape you intend to get, or you're going to get after implementation, and how this shape of the system supports their requirements, whether they are functional or quality and performance related. Also, architectural design is your blueprint, your early blueprint for managing and reasoning about the system, therefore reducing its complexity. Remember I said models usually show you aspects of the artifact being modeled. In our case here, it's software, and suppress or hide other aspects that you don't want to bother yourself with at that stage. Yeah, so architectural design is a way, an essential way for managing the complexity of a large software system. You're stepping back and looking at it at the sort of large grain or the coarse grain components level. So we actually look at software systems as just any other system comprising components and interactions, as you can see here. And obviously within each component can have other subcomponents. So systems within systems, that sort of idea. So you can have a component that is actually accommodating other components or programs, and then in the programs, ultimately we have things like maybe modules and database and files and stuff like that. So this idea of a hierarchy of systems. Again, it's a good way of managing complexity and avoiding getting bogged down in detail. Here's an architectural representation of the software system that would drive a robot for packing. Yeah, so we have a control system that would control that packing robot. And as you can see here, this is like the top level representation of this system. So we need a vision system, so it needs to be able to see things and reasoning about what it's seeing. It should be able to see the package that it's trying to lift and pack. It should be able to see the space of the box it's packing this thing inside, and so on and so on. So the vision system will have to interact with an object identification system. Is this a box, or is this a space, or is this a truck, maybe, things like that. And then we have like another subsystem that comprises the software that controls the arm, as well as the software that controls the gripper, which actually is going to grasp the package. And then another subsystem for packaging. So the packaging will have two parts. One part selects the packaging, so it's got some reasoning ability to select which packaging type is going to use, and the part that actually does the actual packing. And then there's a conveyor controller, because obviously it puts the packs onto a conveyor belt of some sort. Now this gives you an idea about what we mean by representing things architecturally. So this is like at the top level, at the sort of subsystem level, maybe going one level down to describe the components in each subsystem. Again, the main components. We're not sort of doing objects or classes here, or even programs, just bundles of programs or software or classes that would achieve these generic functions as viewed from the domain. So this is a view that is not about the technology, it's about the main parts of the system that would achieve the functions that the users want and that you've agreed with your stakeholders. I've put a couple of question marks here, because actually I don't like this representation very much, simply because the arrows are lacking in the documentation. There are no labels to tell us what sort of things being exchanged on these arrows, or these data flows, or these control flows, what is being exchanged, and so on. So this is showing the major components and the links between them, but obviously it's better to annotate the links so that the diagram is clearer and easier to understand. Otherwise, you just leave it with some ambiguities, which is not a great thing to do. Now we can think of architectures as being either architecture in the small, where we have individual programs, and at that level, thinking about the program architecture, we're looking at how the program is decomposed into components. I actually prefer to call this structure. So program structure, as you saw in one of the lectures, we had a structure diagram, would describe the internal structure of a single program or component. Yeah, but when we go above that level, it's proper to call it architecture, because it's coarse grained, it's holistic, it's like it grows, it's wide, and so on. Okay. Again, the advantages of representing your architecture explicitly, and I deliberately use this term explicit. It's visible, it's open. People in your team can look at it and can understand it and can interpret its meaning. Obviously, one of the first advantages is that it's good for communicating with your stakeholders, and stakeholders viewed widely. So users, your clients, people who commission the system, people who are interested in the system, who have a stake in your system, have an interest, could be government agency or something. Yeah. So the architectural representation is a focus for discussions, debates, and negotiations amongst stakeholders, and of course with the developers team as well, the engineers team. Another advantage or use of representing architecture explicitly, not in your head, I mean explicit as opposed to having it like in your head implicit, they're not telling anybody about it. You're making it explicit, you're making it inspectable, understandable. It gives you the means by which you can analyze your designs to see whether your system would deliver the functions you are desiring. One very important aspect of this analysis is about the non-functional properties or the quality properties, which we will call later perspectives as well. It's another valid name for it. I'm interested, for example, in performance, in dependability, in reliability, in availability, security, safety. These sort of properties that are not directly related to specific functions are like cross-cutting concerns, and you want to analyze the architecture to see if it's capable of supporting these non-functional requirements and perspectives that you and your stakeholders are interested in. One other important advantage of the architecture is that it supports large-scale reuse. I remember we mentioned things about reuse when we discussed object-oriented modeling, that the idea of class and class hierarchy supported reuse, the encapsulation of functions and data into objects that facilitated reuse to some extent. We have here another type of reuse at the architecture level, large-scale reuse. For example, you may pick up an entire architecture that is suitable for a particular domain, which we call a reference architecture, and you instantiate that for a particular company or example of the system. For example, the architecture of the software that would manage airline tickets reservation. Yeah, would have a reference architecture that is sort of proven, tried and tested. So instead of reinventing the wheel, we can start from some architecture that has already been used and proven valid and useful and what have you. Therefore, we can start from there instead of having to carve a new architecture afresh. Also, we reuse architecture. Architecture enable us to reuse our designs at a large scale in the concept of product line architectures, where we have a product line with different variants and different versions. And instead of having to redo the thing from scratch every time when we come up with a new version or variant for a particular client, then we can simply manage this variation in the instances and the variants and the versions and the services offered by a product like, for example, Microsoft Office. So this would have a product line architecture, and then you can sort of replace and unplug and plug things for various customers, various versions or various levels of service. Like there's a professional version, there's a personal version, etc. You don't need to redesign every version from scratch. So that's simple. Called this product line architecture. Yeah, a number of related products with minor or significant variations, but they're all the same product more or less. So the architectural representation helps you manage that. Okay, I mean, how do we represent architectures? I'm going to skip these two slides because they're just very straightforward about what people normally use to represent architectures, and obviously they can be a bit informal, just relying on block diagrams, etc. And there are specific language like architectural description languages, for example, that would have specific notation to describe the components and the subsystems involved in a particular software architecture, but we will not get into these in this course. So box and line diagrams tend to be very abstract or too abstract. They don't show enough of the nature of the components, relationships, or the externally visible properties and qualities that that should be generated by this configuration of components that you've decided upon in your software architecture. Okay, however, again, even if it's informal and not terribly tight semantically in terms of its meanings, using just simple box and line diagrams is still very useful in communicating with stakeholders and for project planning. Yeah? We're not sort of going to generate systems from them yet, unless, of course, you remember the bit I mentioned last time about executable UML, but that's again down the line. It's not at the architectural level still. Well, I'll show you a couple of diagrams that represent some kind of system architecture. Again, at the global coarse grain, coarse as in rough, coarse grain level of what the system contains, and something about the interactions. Another system architecture example. Yeah, we'll say, okay, we've got a central sort of suite or subsystem that has all these components in it, and it interacts with the presentation layer. And then there's something called service layer, which interacts with other pieces of software or services, web-based service in that case, or cloud-based services. And as a result of this interaction, we will have certain types of functions. Again, I prefer labels to be added to this diagram to explain exactly what is exchanged if it's not obvious from the diagram. Sometimes it's obvious, so you just leave it. Here's a kind of representation of architecture. Not everybody agrees with this, but you could sort of divide up your software into various layers, various coarse grain components, and this would be a notation, this package notation, this particular symbol represent packaging in UML, and you can allocate your various components to packages and just describe how these are interconnected. So it's a very simple representation of this software architecture, which is layered in this case because you have databases and then things to manage the entities in the database, and then some control package that would have the business logic as in here, and then boundary or interface package that would manage all the interfaces with the users and external systems. So we're dividing up a large software system into categories of components that are packaging together, and this packaging aims to make the system more resilient against change, more flexible if you want to add new requirements, etc., without having to modify other unrelated components, which you'd have had to do if everything was sort of intertwined and you're not separating concerns in individual visible self-contained package as you see on this diagram. Right, component diagrams, again, it's a kind of aid in representing architectures. Now, components is what you would have inside the packages. So every package would encapsulate or encompass a number of components. So they're like, they're an executable part of the system or implementable part of the system. Could be a program, a database table, a file, something that does something useful, and it's self-contained, and it has these sort of interfaces. So these two rectangles that come out of it represent interfaces of this component. So this component is like encapsulated, and you can only use it via its external interface. It's like an object, but maybe it's a coarse-grained object or a larger object that you'd normally have. And again, this is mapped onto packages or sort of physical bundling of these components as you see here. And finally, you could represent the architecture. This would be the physical architecture if we come to the stage of deploying diagrams. So the deployment diagrams, where you actually decide to deploy particular packages onto what we call nodes or actual hardware and implementation components like a database, warehouse, a server, or a printer, etc., etc. So this would be like the final mapping of where every package is implemented, because here in the package diagram, we're not saying anything about how we're going to implement them or where we're going to implement them. They're just still at the logical level. Just dividing up the software into its packages, and every package will accommodate a number of components, as I said here. And finally, map your packages into actual what we call nodes in this case. And this is the deployment diagram. The deployment diagram you can use to express your intentions about your decisions about deploying your packages onto actual implementation components. So, for example, you might decide to deploy the invoice and the customer components onto the core database server. So you know that this is where these data elements are going to be hosted eventually in the core database components. So you have like a file or a part of a database looking after or modeling or representing invoices, another one representing customer data. So this would sit on the customer corporate database server. So it's basically saying that this node, this implementation node, would contain these components by way of deployment decision. Okay. I said something about facilitating discussions, communicating with the stakeholders is really important in project planning. The support is because it's not cluttered with detail. Remember, if you want to reduce complexity and be able to think clearly and not make mistakes and not get overwhelmed by details that are not relevant at this stage of design, then you want a diagram that sort of abstracts away from these details. Yeah, just leave them to one side. I'm not saying they're not important; they will come back later, but don't want to bother ourselves with these at this point. Yeah, and again, these need to be understandable, and stakeholders need to be need to be able to relate and understand these views of the system, because you want them to give you feedback. You want the stakeholders and collaborators to give you feedback. Okay. Also, documenting the use of architectural models is a way of like the models. I mean, like the diagrams I've just shown you. They're also useful for documenting an architecture that has been designed. Remember, documentation is absolutely vital in software engineering. We're not developing software just to work and perform a function. Now we want a software system that can be later modified and extended for other uses and for other adaptations and other types of maintenance activities. Absolutely important. So architecture becomes one type of documentation or one level of documentation of the entire software system. So that will be like a high level of documentation, the coarse-grained components of the system. So the aim in the documentation activity is to produce a complete system model that shows the different components involved in the system. You could call them subsystems as well, their interfaces and their interactions and connections amongst each other. Okay, architectural design decisions. What sort of architectural design decisions you need to do, and in which architectural representations and models would help you? Architectural design is a creative process, and the process differs the exact process differs according to the type being developed. So I will not describe detailed ways of carrying out architectural decisions. However, there's a number of decisions that would affect all types of components in the system. Yeah, because there's a number of common decisions, or what we call perspectives area, that would affect many types, many sides, or all processes in the system to realize or achieve certain non-functional qualities and characteristics of the system. Yeah, so a number of common decisions would affect everything that you have in your entire software system. Now, I need to say that architecture is not just about getting software that works. Obviously, it will need to work ultimately, but it's about optimizing the design, coming up with the best design decisions that would achieve the various qualities and properties that you need to be present in your software system. This is to say that you can actually cut up your software in a number of ways that are all computationally equivalent. They do the same job. So, we need to say there's something else that architecture gives you other than just an architecture or a software system that works and delivers functions. Now, maybe you want to think about this for a bit. How do they differ? If many architectural solutions for the same system or problem are actually computationally the same, they do the same thing, they achieve the same function, how are they different? Just take a minute to think about that. Okay, you can design your system to be something like that. Lots of interacting components, and everybody is talking to everybody else. Yeah, it's an end-to-end connection. Too many, obviously, it's very complex. It's very hard to reason about whether this is satisfactory or not. Very hard to inspect and validate and verify, especially the verification bit. If you need to effect a modification or maintenance activity or maintenance task, it can be literally a nightmare, and you only have like 7 modules here because you've allowed all modules to interact with all other modules. Now compare this to this arrangement. Instead of having sort of an end-to-end set of connections, we're going to organize them into layers and just control the number of interactions a little bit so that every layer is only allowed to speak to the layer beneath it or above it, not to everybody else. By this very simple action, we just reduce the connection, the potential connections, from 21 connections on the previous diagram to just 13 on this diagram. So it's about half of the connections that we had before, therefore roughly about half the complexity and the interactions. The interactions have also dropped by almost a half, by about a half. So these decisions, these structuring decisions, can affect a number of properties in the system. In this case, we're seeing the effect of complexity and the increased maintenance load and complexity of the maintenance activities afterwards. I mean, complexity affects you in 2 ways. One is when you inspect the system to make sense of it, to verify it, to make sure it's working properly, and it affects you when you want to make changes to the system, either to rid it of bugs or improve it or adapt it or adapt it to a different platform, or make it better and increase its performance. It'd be extremely hard to perceive, grasp, or understand something that as complex as this. A lot harder than trying to do it with a much more simplified and less complex arrangement like the one you can see here. Obviously, maybe you can even simplify this even further. Yeah. But here we have in this sort of layered architecture, which we'll come to later, every class can only speak or interact with adjacent classes, not cross and jump classes. Therefore, you're reducing the complexity of each individual module because it doesn't have to speak to many others. This is important. So even the internal complexity of each of these modules is improved. It's reduced. Now, an architectural representation, the visual architectural representation like this, helps you make decisions that involve trade-offs. Many design decisions involve trade-offs. Trade-offs as in you cannot have everything. You cannot optimize in all directions similarly and simultaneously. You know this example about, you know, you take a piece of material to your tailor and you want a new suit or dress or whatever, and you cannot have it done cheaply, quickly, and at a very high level of quality. You know, you can always ask for two of those at a time, but not all three. So we have this triangle of do you want to achieve the maximum quality and how much speed? Yeah, because you have short time to market and so you're under some kind of time pressure, or low cost. You cannot have all three at the same time. You cannot have it immediately to market at a very low cost and with the highest quality. You have to compromise. You have to cut corners in one of these directions to be able to achieve the other two. So you're giving priority, in this case, you're giving priority to a high quality system, which obviously will push the cost. But if you don't want to push the cost so much, then maybe you need to sacrifice a bit of time and lose a market window, or get to the market after or slower than your competitors. So it's a price you have to pay. Now again, architectural representations, architectural reasoning at the level of architecture helps you make these decisions and make these comparisons and trade-offs, because you can more easily, not totally easily, but more easily establish the effect of going for higher quality and very fast delivery, for example. Yeah. So you can actually say, okay, I can, at this level of reason, I can say, okay, then maybe I can sacrifice something to get something else. Like, for example, in the reference architecture, sometimes you have to make sacrifices and not follow it to the letter because you want to make efficiency gains somewhere else. Is the range of architectural design decisions that you need to make, and where architectural design representations support you. You make a decision about whether there's a generic application architecture that can be used, that can act as a template. How will the system be distributed across hardware, processors, or just hardware? What architectural patterns or styles might be used and would be most effective and most appropriate to the problems at hand? What strategy to use to control the operation of the components of the system, as in control flows and allowing things to operate or not. Maybe you need something to control synchronization and prevent parallel running or simultaneous running of some components, and so on and so forth. You need to make a decision about the documentation of the architecture. You need to decide on what organization would be best to serve your non-functional requirements and qualities. What would be the fundamental approach used to structure the system? Is it top-down? Is it bottom-up? Is it middle-out? These are all strategies for cutting up or deriving the detailed architecture of the system. How will the structural components of the system be decomposed into subcomponents? I've got a problem here that sort of some of it is using structure and architecture interchangeably, as if they are synonyms. They're not. I think that architecture is at a higher level than the structure. So structure diagram is not the same as an architecture diagram for a program. But okay, let's move with that terminology, knowing that it might not be the best one. Okay, this is basically the same thing that I showed you in this diagram. Architecture reuse. When you have sort of proven and properly working architecture, maybe you can apply it elsewhere to similar applications. So these architectures act as templates you instantiate for different organizations. We've already done a bit of that, but maybe the new thing to mention here is the idea of an architectural pattern or style. For example, the layered architecture serves as a useful generic template that captures an essential organization that can be useful for certain types of systems with certain gains in terms of the qualities of the resulting system. One example is this, the OSI, Open System Interconnection reference model architecture for networking. Maybe you've seen that before in a networking course, but the idea here is that this layered architecture allows only every layer to interact with the one directly adjacent to it, with the advantage that, for example, in a network, this is about networking, if your physical medium changes, for example, the physical medium changes from a copper wire to a fiber optic physical connection, you don't have to change the application because your application is isolated from these lower layer body and intervening or mediating layers in between them. So we have these sort of seven layers, and the changes in any one of them would be limited to that layer and the one directly above it or directly underneath it. So you don't have to mess about with lots and lots of components and find that maintaining the whole system for changing one of the layers becomes extremely complex and unwieldy, which will make it very hard to implement, give rise to more probability of errors, as well as make it very time consuming and effort consuming as well. So this is like an architectural style or template that people have been using for other types of applications as well, but certainly it is very useful for the networking pursuit or connecting data with each other. Okay. Architecture is your fundamental means of reasoning about the system characteristics. These would be the emergent system characteristics or properties. So as a result of you making certain architectural choices, you get certain levels of performance, of security, of safety, of availability, maintainability, and so on. Remember, you cannot achieve all of these characteristics and properties to the maximum level because there are trade-offs. For example, performance, the performance objective might mean that you minimize communications and place as many components as possible on single nodes, to reduce communication overheads. But that would compromise something like availability, because if that component breaks down, you've lost your system. So it would be better from the availability point of view to have redundant components and some distribution so that the system can still gracefully degrade, if you remember that term from the beginning of the course. You want your systems to degrade gracefully, achieve graceful degradation, i.e. if one component does not propagate to the rest of the system so as to shut it completely down. So some of these characteristics and features actually work against each other. You cannot achieve maximum performance and at the same time maximum availability and maintainability. You'll have to make some sacrifices in one of these. Hence, this sort of this kind of triangle or triangle-like representation that says you have to make compromises in one area or more. So that's what the sort of the delight of design and the tricky thing about design, that you're always actually making trade-offs and making sacrifices to achieve other important factors. Okay, so what should you do then? Well, if you understand the domain, if you understand the clients and requirements very, very well, then this becomes a bit easier because you understand from the point of view of your particular application, particular system, particular organization or client that you're serving, which of these characteristics would be most important, most vital. Okay, architecture views. But we've seen these before. One of the decisions we have to make is to decide what views or perspectives are useful when designing and documenting systems architecture. I made a bit of distinction between views and viewpoints. I said the viewpoints are like, where you're looking at the system from, like a functional viewpoint, and the actual views is the instantiation of that viewpoint. And what notations should you use? Now, each architectural model usually shows one view, one perspective of the system. Yeah, so for example, a particular model would show how a system is decomposed into subsystems or components, and how the runtime processes in the system interact with each other. But for both design and documentation, you usually need to have a number of these views on the software architecture, and each representation will describe one of these, not all of them at the same time. Otherwise, things will get very, very complicated. So let's look at something we saw before when we discussed Christian's view, that we have logical, physical, process, and development views. And I sort of gave you a bit of an annotation on each of these, saying who is the audience for each of these views. So for example, the development view would be the software developers themselves, as well as the software project management, that is. Okay, so you can read these again, they're not very different from what we discussed before, but in the book by Rosansky and Woods, I'm actually very proud of it because Rosansky, Ian Woods, was one of my students at Birmingham University. I met him a few months ago in the UK, and I sort of, I congratulate him on this book. It's really a very nice book of software architecture. I'll put the reference at the end of this lecture. Again, we can have these views. Functional viewpoint, yeah. Obviously, this is of most interest to the users and stakeholders. Concurrency viewpoints, are you gonna have all your functions being served using concurrent components or not? Sometimes they merge these views as well. So the functional view is the same one as the concurrency view, which is to say you don't have to have exactly these types of viewpoints in your software. Again, you decide on what are the salient or important viewpoints to your system that you need to show explicitly and reason about. Yeah, so that's how this works. The information viewpoint would be concerned with the data and data organization. Development viewpoint, we talked about that before. The software developers and cutting up the software system into components that they're allocated to work on. Deployment is about the actual physical deployment of the system onto hardware and technological components. So that'll be the deployment of your packages and components in terms of software onto actual hardware and technology elements. A scanner, a printer, a device, a database, camera, what have you. And then the operation point of view, how is this system is going to be actually operated. Here are some relevant terms that I think are interesting. Here we have a distinction between the viewpoints and the views. As I said before, the viewpoints are where you're looking at the system from, and the views are the actual instantiations. So the viewpoints are the approach to structure the architecture, to divide up the architecture definition process. So you don't have everything at once at the same time. Yeah, and the architectural description of your system into distinct or not distinct, related of course, but they're different, they're separate, used based on the principle of separation of concerns. So for example, the informational view here would be interested in the database and how's the data structured and organized. This is separate from where I'm going to deploy this data, for example. So the deployment view would, or viewpoint would give you an opportunity to express where the information components are going to be actually deployed on databases. Is that database just one database? Is it a distributed database? Even what kind of database engine and so on? So we're trying to separate concerns. We're trying not to decide everything together at once. We want to keep things separate so that we can reason about them, and we need to maintain them separately as views, so that if we maintain the viewpoints later on because of some change, we don't want to have to bother with so many other viewpoints simultaneously at the same time, which gives rise to confusion and errors. Yeah, stakeholders, you would have seen that. You have seen that before. And here you see a definition for viewpoints that contain proven architectural knowledge to guide the creation of the architecture. Like, for example, I want to look at the system from this viewpoint, from the concurrency viewpoint, because I know it's important and would affect certain aspects of the system qualities of the system. And this would be documented in views. So each view is an instantiation of a viewpoint. It's the result of applying that particular guidance to include the particular viewpoint. Yeah, so the view is the actual physical instantiation of the viewpoint. So it's a result of applying the perspective or the interest expressed in the viewpoint because we think it's important. Now, Rizalsky would make a distinction between viewpoints and perspective. It's worth saying, you don't have to adopt it, but it's worth getting to know, because perspectives to them are about the cross-cutting qualities of the system. So they say it's perspectives are a complementary concept to viewpoints, but these focus on cross-structural quality properties across the entire system. So it's like a cross-cutting concern if you know something about aspects and aspect-oriented development, which we didn't discuss in this course. But cross-cutting means all components in the system, all views in the system will have to be concerned with this in some way, or we have some concern with this in some way. For example, security, you would worry about that in all the views of your system and all the representations and structures and architectural views of your artifact. So these would be perspectives. Let's just, for simplification, just consider them to be the properties or close to the non-functional properties that we discussed earlier. One thing very important about cross-checking, if you remember from the models lecture, we need to cross-check our models. And the models express the views, don't they? So the views are documented as models. So we have models that correspond to functional viewpoints, contextual viewpoints, deployment viewpoints, hardware, operational viewpoints from the user's perspective, how they can operate the system. We didn't have this as one of the models before, so this is new. Information, concurrency, and so on and so forth. There are mappings and connections and dependencies between them. Yeah, so you need to be aware of the dependencies, and you need to make sure that these viewpoints or views actually correspond to each other. So the viewpoint is like contextual viewpoint, but the actual view contained once we instantiate that is the actual context of a particular system. So for example, we map the context of the function and make sure that the functional view actually is aligned to the contextual view and so on. So there are some dependencies between them which you need to be aware of and careful about. Here's a definition of perspectives. An architectural perspective is a collection of architectural activities, tactics, and guidelines that are used to ensure that the system exhibits a particular set of related quality properties that require consideration across a number of systems architectural views. Yeah, so these are properties that require consideration across a number of systems architectural views. So all of these views are relevant or will have something to say or some concern about the perspectives that you want to make sure is realized in the final software system. And these the views correspond to what we previously referred to as functional requirements. So what perspectives do we have? Security, dependability, performance, and so on. Architectural patterns. Now, architectural patterns are means of representing and reusing architectural knowledge about software. They're like your generic templates. They're like a pattern that has proven to be useful and effective elsewhere in other problems, other similar problems, so you want to be able to use it again. An architectural pattern is a stylized description of good design practice, which has been tried and tested in different environments. Yeah, so it's something good. It's a good solution that works, and we want to be able to reuse it. So we give it a generic description so that we can easily compare it to other patterns and decide whether this particular pattern is useful or not. So it has certain documentation as well. So the patterns should include information about when they are useful and when they're not useful. There are many representations of patterns. We'll see one in a minute. Here's another definition of architectural pattern from another textbook. An architectural pattern is a set of architectural design decisions that are applicable to recurring design problems or to a recurring design problem. For example, maintaining data, that would be a recurring design problem. So there's a pattern to help you organize the software that would maintain and take care of data on the database. And these are parameterized to account for different software development context, yeah, because the context will be different. So there are parameters or variation points so that you can actually adapt the particular template or the pattern to a particular software design problem. A widely used pattern, for example, in modern distributed systems is the three-tiered or the n-tiered pattern. The three-tiered is the sort of classical data, business logical rules, and presentation. We'll see something like that very shortly. Okay, here's a documentation of the model view controller pattern. Let me read the description with you. What is the MVC or the model view controller? It's a very popular software architectural pattern. It separates presentation interaction from system data. Yeah, so leave the system data alone, take the presentation interaction in separate modules or components. So the system is structured into three logical components that interact with each other. The model component manages system data and the operations to maintain it. The view component defines and manages how the data is presented to the user, and the controller manages the user interaction and passes the user interaction to the view and the model. So it's a way of dividing up, structuring the architecture in a way that makes it more maintainable, more flexible, because you're separating the concerns. You're not binding everything together. You're not merging everything together. And this is a graphical view of how that might look like. So a controller manages or transfers the user actions and the changes in the data to the model. So this is the data. Yeah, so this like has the logic of what happens to the data, or relays requested changes to the data based on what the user actually does. Yeah, and the view is basically how you're going to present these views, this data, and the controlling abilities or control actions to the user. So it's like a rendering of the model, of the data that's in there to the user, and send the user events to the controller. Yeah, so this is like the interface. So the view is like the interface, like maybe your web browser or your screens and menus that you manage operations in the software system. So it relays these events, the user events to the controller, and the controller executes these kinds of events, obviously guided by the business logic and the business rules, and what allow what user actions are permissible or not. For example, like when you have on a web browser, yeah. So here's the browser, and it obviously presents the views to the users, and uh, the views of the user manages. Um, um, by the views, the user issues commands, makes requests. The controller executes these requests by interacting with the model or the actual database. Sometimes we put a bit of the data of the business logic in the database. This is really like a moot point. So don't think that what I told you earlier about the controller having some business logic is wrong. Sometimes we place some business logic with the database, but you obviously have to be very careful. It's when you have something like active databases or databases that have their own logic to maintain the data, ways of maintaining the data. It's best to keep this as thin as possible, because if the business logic changes, you don't want to reprogram or re-implement your database. So one very important achievement or advantage here is that you're keeping things separate. Yeah. For example, if I merged or mingled the view constraints with the model, the data, if the view requirements or the constraints change, I'll have to mess about. I'll have to intervene and change the model as well, which is highly undesirable. It increases the maintenance effort tremendously, as well as gives rise to errors being introduced. You don't want that. So by keeping things separate as much as you can, well-defined interfaces, so that as much as possible, you localize the change into a small compartment or to a well-defined compartment. You don't want the change request to propagate to other parts of the system unnecessarily. So this is a fundamental structural mechanism here, and it's like a logic or recommendation or design principle that propagates everywhere else in software engineering, keeping things separate to minimize the maintenance effort. Okay. One sort of famous pattern as well. There's a description here, which I'll leave you to read it, but let's look straight at the representation again. Here, a generic layered architecture, layered software architecture. We're keeping the user interface separate from the user-related controls and the interface management, authentication and authorization and feedback and what have you. And the business logic, the core business logic, is separate from the underlying technologies and maybe including the databases here as well. Why is that? If the business logic changes, and this is likely to happen, you don't want to have to redesign the database, do you? You don't want to have to replace the operating system entirely, do you? So keeping things that are more likely to change separate from the things that are more stable and long-term in terms of their susceptibility to change or volatility, if you like. Whereas the user interface, okay, we may request user interface changes often, so why not keep that separate? So again, localizing the effect of change, localizing the interference in a particular layer of the system, and trying to contain that within a single layer as much as possible to minimize the effect of change on the rest of the system, which gives rise to more maintainable system. So this is a layered architecture of separated user interface from user interface management software and things like validation, authentication, authorization, which is again separate from the core business logic and the application functionality, and the application functionality which might change often because of new requests from the management or what have you. These are separate from the underlying utilities and the system support components like a database. This is an example from a system called iLearn. It's a learning, an online learning system. Again, we have utility services that are separate from the applications, and these are separate from the configuration services which compose groups and types of courses, etc., manage identities of students and students, and all of these are separate from the browser-based user interface. So we've bundled up the types of components that are required in the system into separate layers. And the layers are like coherent, they are strongly related to each other, they change together. Yeah. So the things that are likely to change are separate from the things that are less likely to change. Okay, and this is a layered architecture that would help you localize the effect of any particular change to within that layer as far as possible. It's not like a foolproof or guaranteed thing. Okay. Right, so in this lecture, what we were on about, the key points we discussed is that software architecture is a description of how a software system is organized at a high level. Yeah, and it's not all in a single diagram or single representation. We have different views. Architectural design decisions include decisions on the type of application architecture, the distribution of the system, and the architectural style to be used. Architecture may be documented from several perspectives, yeah, or viewpoints. Actually, I'm just going to highlight that, and be careful that perspective can mean different things in different texts. Or views such as conceptual view, the logical view, process view, and independent view. In fact, the word view here is used as a synonym to viewpoints. Yeah, I made a bit of a distinction between views and viewpoints. Here on this particular slide, views is used in the sense of a viewpoint, a way of looking at the system, not an instance of a viewpoint. Yeah, like not an actual design, for example, or an actual development design, for example. Architectural patterns are means of reusing knowledge and architectural knowledge and system design knowledge about the generic systems architectures and their properties because we find them useful, proven, etc. So we might want to use them in similar applications or applications that could make use of these architectures. The patterns describe the architecture and explain when they might be useful or not, and describe the advantages and disadvantages of particular patterns. Okay, so I'll stop here and we carry on in the next lecture, inshallah. Thank you very much.